In this video, I will be discussing about articulation points. They are also known as cut vertices, and the algorithm that is used to find articulation points is known as Tarjan's algorithm. Before proceeding with this algorithm, you should be familiar with the graph terminologies. If you have any doubts on that, please refer to the suggested video on the top right corner. Now let's proceed with articulation points. So a vertex is called an articulation point if removing it and all the edges associated with it increases the number of connected components in the graph. So in this graph, the articulation point is C. If we remove this vertex and the edges that are attached with it, we remove BC, AC, DC and EC edges. So that will give us four different components of the graph. So it will be A, B, D, E. So the number of connected components has increased. So we can say C is an articulation point. If we check in the second graph, if we remove C, then we have to remove all these edges. So the connected components remain AB and DE. So we'll get two connected components if we remove C. And if we remove D, so the two components that we'll get is one connected component will have ABC and the other component will have only E. So this also increases the number of connected components. So in this graph, C and D are articulation points. Now articulation points have a lot of applications. So to detect the critical points in communication, airline traffic, electric circuits, we use articulation points. So these are the single points of failure in these networks. Now the other term that is used along with articulation point is biconnectivity. So a connected undirected graph is biconnected if there are no vertices whose removal disconnects the rest of the graph. So in short, it means that there are no articulation points. So if we see this example, there are no articulation point in this graph because if you remove the C vertex and the edges that are attached with it, you will get the graph like this. If you remove A, you will get the graph like this. So the graph is still connected and the number of connected components has not increased. So in this graph, there are no articulation points. So whenever there is a case, we can say that the graph is biconnected. So now let's find out the algorithms that are used to find articulation points. So first we'll discuss the brute force algorithm. It is not very efficient as it takes a lot of time, but still it is good to know that what is this algorithm. So basically what we do in this algorithm is we remove all vertices one by one and see if removal of that vertex cause disconnected graph. First we'll remove any vertex. Let's say we remove vertex A and we remove the edges that are attached with it. And the rest of the graph is there. We do a BFS traversal on that graph and we check that whether the graph is connected or not. So the pseudo code is quite simple for this one. So first we keep a result array in which we'll store the articulation points. Then for each V in the vertices, we remove that vertex from the graph. We check whether the graph remains connected. If it does not remain connected, we append that vertex to the result. And in the check connected function, we can use either BFS or DFS traversal. So if you have any doubts on how we can do a BFS or DFS traversal, I have made a separate video on that. I will link that in the top right corner. You can have a look. So it is just to get an idea of how the brute force algorithm works. So the time taken in this algorithm is order of V plus E is for the BFS traversal or DFS traversal, and we will do it for all the vertices. So it will be order of V into V plus E. This is very inefficient. For dense graph or graphs that are large in size, this will take a lot of time. So to solve that, we have another algorithm which is quite efficient, and that algorithm is known as Tarjan's algorithm. So now let's have a look at what is Tarjan's algorithm. So Tarjan's algorithm says that in DFS tree, a vertex U is an articulation point if one of the two conditions is true. So the first condition that it finds out is if U is the root of the DFS tree and it has at least two children. Let's say the DFS tree is something like this. If we remove this vertex and the edges that are attached with it, we'll get two different components of the same graph. So that means U has to be an articulation point. So the first condition is quite simple to understand, is that we have to just check that whether root is node of the tree and it has more than one children. If the condition is true, that means that node is an articulation point. Now the second condition is a bit tricky. So second condition says that U is not root of DFS tree and it has a child V such that no vertex in subtree of V is connected to ancestor of V using a back edge. So before we try to understand what the second condition means, we should know what do we mean by back edge. So back edges are those edges which are present in the graph but are missing in the DFS tree. So let's first draw the DFS tree for this graph. So we'll start the DFS traversal from A, we'll go to B, from B we'll go to C, from C we have two options, let's say we go to D, from D we go to E, from E we go to F, from F D is already listed so we have to backtrack, so we backtrack till C and then we reach G. So this will be DFS traversal for this graph and this is the DFS tree. Now back edges are those edges which are present in this original graph but are missing in the DFS tree. So we see that there are two edges that are missing. One is between A and D and one is between D and F. So these will be back edges. So whenever we are drawing back edges direction will be from bottom of the tree towards top of the tree. In the DFS tree, D is downwards of A, so the back edge direction will be from D to A. Similarly for F to D. So let's try to find out the articulation points using condition number 2. So the first point says U is not root of DFS tree. So we'll skip node A because it is root of the DFS tree. So now we come towards B. It has a child V, so C will be V. So the subtree rooted at C has a vertex D that has a back edge towards ancestor of B. So D has a back edge towards A, so B cannot be an articulation point. Now let's come towards C. So C has a vertex G and no child of G has a back edge towards ancestor of C. So C will be an articulation point. An important point to remember is that leaf nodes can never be an articulation point. So G and F can never be articulation points. Now we come towards D. So D has a child E. Now subtree of E should not have a node that is pointing towards ancestor of D. So we have a back edge from F, but that is pointing towards D, not to ancestor of D. So D will also be a articulation point. Now we come towards E, but for E, there is a child F that is pointing towards ancestor of E. So E will not be articulation point. F is a leaf node, it cannot be articulation point. G cannot be articulation point. So the articulation points in this graph are C and D. So by this method, we can find the articulation points in a graph. So the Tarjan's algorithm says that for each node, we have to compute two things. First one is the discovery time. So discovery time is nothing but in which order we are discovering these nodes. So first we are discovering A, so we are given the time of 1. Then we discovered B, so we have incremented the timer to 2. Similarly, then we explored C, then D, then E, then F, and at the last we explored G. So we're just incrementing a variable and that we'll consider as discovery time. So it is just a notation to keep track of the order in which we are visiting the nodes. The second thing that we have to compute for each node is the low time. So low time means time of the earliest node that can be reached from subtree U. If we have to find low time for a particular node U, then it will be a minimum of 3 variables. First is the discovery time of U, so this is the discovery time. Then discovery time for the back edges which are visited from that node, and for all the children of U in the DFS tree. So let's try to find the load time for each of the nodes in this DFS tree. So what we'll do is we'll first try to find the minimum of these two values, and then once we have the low value for all the children in the DFS tree, then we can revisit and adjust the low values for all the nodes of the graph. So for 1, there is no back edge and the discovery time is 1, it will be 1. So for B, there is no back edge and discovery time is 2, so it will be 2. For 3, there is no back edge, discovery time is 3, so it will be 3. For 7, no back edge, it will be 7. For 4, we have a back edge which is pointing towards A and disk of W. So discovery time of A is 1, so it will be minimum of discovery time of D and discovery time of A, so it will be 1. So for E also we have no back edge, so load time will be equal to discovery time. For F we have a back edge towards D and discovery time of D is 4, so it will be minimum of 6, 4, so it will be 4. Now once we have load time for all the nodes, then we can check this third condition, that the load time for the parent should be less than for all the children in the DFS tree. So now let's again revisit this. For A, load time is 1, which is lesser than all the nodes which are child of A. So 1 is fine for A. Now load time of B is 2, but it has a child D, which has a load time of 1. So we have to adjust the load time to 1. For C, load time of D is 1, so we have to again change it to 1. For D it is fine because it is already minimum of all the childs. So E has a child F which has a load time of 4, so we have to again reassign load time of E to 4. So these are the final load times that we have calculated for this DFS tree. So once you have calculated the discovery time and load time for all the nodes in the DFS tree, then the second condition of the Tarjan's algorithm can be rewritten as, if discovery time of a node U is less than or equal to load time of a child V, then we can say that U node is an articulation point. So now let's see how this condition evaluates in the DFS tree. The first value is the discovery time and the second value is the load time. So I've written this for all the nodes in the DFS tree. So A is the root of the tree, so we'll skip it. So for B, discovery time is 2 and load time of its child is 1. So this condition is false. So B is not a articulation point. So now we come towards C. Discovery time is 3 and one of its child G has a load time of 7. So this is true. So C is an articulation point. G cannot be an articulation point because it is a leaf node. For D, discovery time is 4 and its child has a load time of 4. So this is also true. So D is also an articulation point. For E, discovery time is 5 and its child has a load time of 4. So which is false. So it is not an articulation point. So the articulation points of this graph are C and D. So once we have found out the load time and discovery time for all the nodes in the DFS tree, then it is quite easy to find out which will be the articulation points. Now let's have a look at the pseudocode of the Tarjan's algorithm. So the data structures that we would require for this algorithm are, first is the result array. So here we'll store all the articulation points. Then we have a visited array to keep track of all the visited nodes. Then we have two arrays for discovery time and load time. An array to keep track of all the parents. So this is required for the first condition of the algorithm, where it states that if it is root of the tree and it has more than one child, then it is an articulation point. So for that we have to keep track of parent for all the nodes. And then we have a simple variable time. So we'll increment this in every iteration. So it will be used to set discovery time and load time. So let's start our traversal from vertex A. So the first step is we mark the node as visited. So we mark A as visited. Then we set load time and discovery time to time plus 1. Time is 0, so both of these will be 1. So let's say we have this function find AP. We call it for A. Time is 1, 1. So first is here discovery time and second is load time. We have a variable child which we initialize to 0. For each adjacent vertex of V, so adjacent vertices of A are B and D. So let's start with B. So if B is not visited, we increment the child. So child is now 1. We set parent of B to A. and we call find AP for B. So now V is B. So a recursive function call is made. So now visited B is true. We set low and discovery time for B equal to time plus 1. So time is initially 1, so it will be now 2. So for B we are setting it to 2, 2. Now for each adjacent vertex of B, adjacent vertices for B are A and C. So let's say we start with A. So if A is already visited, so this condition is false. So we go to the else condition. Here we see that if AV is not equal to parent of V, AV is A and parent of V is also A. So this condition does not hold true. So we check the next vertex of B. So next vertex of B is C. So now AV is C. So since C is not visited, we come in the if condition. We increment the child. We set parent of AV equal to V. So parent of C will set as B. And then we again do a recursive function called for C. So V is now C. We mark C as visited and we set low and discovery time to time plus 1. So it would be 3, 3. Child is 0 for each adjacent vertex of C. Adjacent vertices of C are B, D and G. So let's start with B. But B is already visited, so we come in the else condition. So we check AV is B and parent of C is B. So this condition does not hold true. So we again check the next adjacent vertex for C. So now AV is D. D is not visited, we increment the child. We set parent of D to C and we call find AP for D. Now we mark D as visited and we set low and discovery time to time plus 1. So it will be 4, 4. So for each adjacent vertex of D are C, A, E and F. So let's start with C. C is already visited. We come in the else condition. So here AV is C and parent of D is also C. So this condition does not hold true. We check the next adjacent vertex A. A is already visited. So we again come in the else condition. So if AV, which is A, and parent of D, which is C. So now this condition is true. So we have to calculate low V again. So low of D is equal to minimum of low of D is 4. Discovery time of A is 1. So it will be 1. So we'll reset the low of D to 1. After this we come to the next adjacent vertex for D, which is E. So now AV is E. E is not visited. We increment the child. We set parent of E to D and we call find AP for E. V is E. We'll mark E as visited and we'll set the low and discovery time to time plus 1. So it will be 5, 5. For each adjacent vertex of V, adjacent vertices of E are D and F. So let's start with D. D is already visited and D is also parent of E. So this else condition does not hold true. We check the next adjacent vertex of E. So next adjacent vertex is F. F is not visited. We increment the child. We set parent of F to E and we call find AP for F. So V is now F. We mark F as visited. We set the low and discovery time to time plus 1. So it will be 6, 6. Now for each adjacent vertex of V, adjacent vertices are E and D. So let's start with E. E is already visited. We come in the else condition. But E is also parent of F. So this condition does not hold true. The next adjacent vertex for F is D. D is already visited, so we again come in the else condition. Now the parent of F is E and adjacent vertex is D. So now this condition holds true. So we'll have to calculate low of f, which is minimum of low of v. V is f, so low of v is 6, and discovery time of AV, so discovery time of D, which is 4. So this becomes 4. So let's reassign low of f. So once this is done, we'll have to backtrack. So now we come here. So at this point, V is E and AV is F. So we calculate low V for E, which is minimum of low of E is 5 and low of F is 4. So it is 4. So we'll have to reassign low of E to 4. So once we have reassigned, we come in this if condition. So parent of E is not null. So we come in the next if condition, and low of AV is greater than discovery time of V. So low of AV, which is F, is 4. Discovery time of V is 5. So this condition is not true, so we do not append anything. So from E we again backtrack. So now V is D and AV is E. So we are here. So let's calculate low of D. It will be minimum of low of D is 1 and low of AV is 4. So it is 1. So it was already 1, we do not do anything. Parent of D is also there, so we come in this if condition. And low of AV is greater than discovery time of V. Low of AV is 4 is greater than equal to discovery time of V. V is also 4. So this condition is true, so we append V to the result. V is D, so we append D to the result. So from D we again backtrack towards C. So now V is C and AV is D. We are at this step. We calculate low of C, which will be minimum of low of C, which is 3, and low of D, which is 1. So it is 1. So now we'll have to reassign low of C to 1. And we come in this if condition, parent of C is present. So this condition does not hold true. We come to the next if condition. We check low of AV. So low of D is 1. The discovery time of C is 3. So this does not hold true. We do not do anything. So when we come at C, we see that there is also one more adjacent vertex, which is G. So now this for loop will again come for vertex G. So from here we'll have to call find AP for G, and we'll set parent of G to C. So now V is G. We set low and discovery time to time plus 1. So time was 6, so we set it to 7,7. For each adjacent vertex of V, adjacent vertex of V is C. So C is already visited. We come in this else condition, but C is also parent of G. So this does not hold true. So after this, we have to backtrack from here. So now V will be C and AV will be G. So at this point, we'll have to calculate low of C, which is minimum of low of V, which is 1, and low of AV, which is 7. So it is 1. So 1 was already assigned to C, we do not do anything. Now parent of C is already there, which is B. So we come in the next if condition. Now we have low of AV, which is 7, is greater than equal to discovery time of V, which is 3. So this is true, so we append C to the result. So after this step, we backtrack from C. So now V is B and adjacent vertex is C. We calculate low of B by minimum of low of B is 2 and low of C is 1. So it will be 1. So we reset low of B to 1. After this, we check parent. So parent of B is already present. So we check this condition. Low of AV is 1 and discovery time of B is 2. So this condition does not hold true, we do not do anything. So from B we again backtrack. So now V is A and AV is B. We calculate low of V, low of A, which is minimum of low of A and low of B. So it is 1, 1 is already assigned to A. So we come to this if condition. Now parent of A. So if we check here, parent of A is null and child is greater than 1. But A has only one child, which is B. So this condition does not hold true. And this condition also does not hold true. So in this way, this algorithm ends. So the articulation points that we get are D, C. So in this way, by calculating the discovery time and load time for all the nodes, we can find the articulation points. Now let's also have a look on how to implement this algorithm. I'm using C++ and all the code that I'm showing is available in my GitHub repository. Link of that is available in the description. So now let's jump into the code. So we start with creating the data structures. So first we create the graph of 7 vertices. We keep a visited array and we keep a parent array. I've initialized all of the parents to -1 and 2 arrays for load time and discovery time. Then we create the graph. So it is undirected graph. So in the add edge function, I'm adding both sides from U to V and from V to U. So this is an edge from 0 to 1 and from 1 to 0 for 0 to 3 and 3 to 0. So in this way, I have initialized the graph with all the edges. I've created a set result. So here I'll be storing all the articulation points. And then I call this function find articulation points, in which I pass the graph, discovery time, load time array, visited array, parent, result, and the start vertex. So I'm starting the traversal from 0. So in this function find articulation points, I mark the node as listed. I have kept a global variable time which I've initialized to 0. So I increment the time, and like in the pseudo code, I set the discovery time and low equal to time. The variable child is 0, and I traverse all the adjacent nodes for this vertex. I check if it is visited. If it is visited, I call the articulation point for the adjacent node, and then I adjust the load time accordingly. Then I have two conditions, both for the condition 1 and condition 2 of the Tarjan's algorithm. So this if condition is for the condition number 1 of the Tarjan's algorithm. When node is root of the tree and child is greater than 1, we add it to the result because it will be an articulation point. And this else condition is for condition number 2. So when either of these condition is true, I add it to the result. And then when visited is true, so here I'm checking the back edges, and if a back edge is present, I adjust the load time, comparing the load time and the discovery time. So after this function ends, I'll have all the articulation points collected in this result, and here I'm just printing the result. So I'm printing all the articulation points. So let's see the output of this function. So output is articulation points are 2 and 3. So you have seen that code is similar to the pseudo code that we have discussed. So if you understand the pseudo code is very easy to write. So the time complexity of this algorithm is equal to time complexity of DFS, because basically we're just doing a DFS but just keeping some extra information like load time, discovery time, and parent. Time complexity is order of V plus E, which is the time complexity of DFS traversal. So this was all about articulation points. If you have any doubts or suggestions, please leave them in the comment section below. If you like my content, please like, share, and subscribe to my channel. And until next time, this is Sandeep Thapar signing off.